Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here. Hit the notification bell. What we're going to do is Calculus 2 lectures. This time specifically we're going to do partial fraction decomposition. And the gory details of that is first we're going to describe what a rational function is. Then we need a proper rational function. And then we need to decompose or factor the denominator always. The numerator, don't worry about it. And then once we factor the denominator of a proper rational function, we will use partial fraction decomposition guesses on those decomposed factorized denominators. And then what we will do from there is finally solve. We make these guesses which have constants or undetermined coefficients in them. We will find out how to systematically use linear algebra or otherwise to find those undetermined coefficients, and then we will finally integrate the result. So the idea is integrating rational functions. This is what we want to do, but these will be the 5-step process into doing that. Let's get to it. Okay, a function r of x, R for rational. We're not very inventive when we make our names and symbols, but a function R is called rational if it's the ratio of two polynomials. Basically, I'm hoping you know what a polynomial is. A polynomial is non-negative exponents of x, our single variable. So a of x is going to be a degree n polynomial, and b of x, our denominator, is going to be a degree m polynomial. So any function which is the ratio of two polynomials is going to be called a rational function. What partial fraction decomposition does is it attacks proper rational functions. So we need another definition on what's the difference between proper and improper. If the degree of the numerator is strictly less than the degree of the denominator, we're going to call it proper. So if it's larger than or equal to the denominator's degree, it's just going to be improper. So if it's not improper, or if it is improper, what are we going to do with this? We're going to use long division of polynomials to create a polynomial plus a proper rational function. We'll do that in a second. Let's give the actual definition of what proper and improper is. Okay, so a rational function, a of x over b of x, is called proper if the degree of the numerator a is strictly less than the degree of the denominator b of x. And of course, the parasitic definition is it's improper if it's not proper. That doesn't really help. But what's the negation of a strictly larger, less than or equals? So it's improper if the degree of a of x is greater than or equal to the degree of the denominator b of x. So if you want to use shorthand, if you just call the degree of a n and the degree of b m, then it's proper if n is strictly less than m, and it's improper if the degree is larger than or equal to m, if n is larger than or equal to m. So partial fraction decomposition has to be done on a proper rational function. What happens if your instructors, like me, are mean and give you an improper function? We're going to have to make it proper by using long division. Let's do that. Is it raining outside, or are you just running in the... So what we're going to do with this is, how do I take, if they give you, okay, take it in there. If they give you an improper rational function, what am I going to do? Arms to the sky? Well, at first, yes, probably. But what we're going to do is, how do you transform an improper rational function into the addition of a polynomial plus a proper rational function? We're going to use the division algorithm for polynomials. Theorem: for any two polynomials, a of x and b of x, we're going to assume in mind that a is always the degree larger than that, because it's going to be improper. We can write a of x is q of x plus b of x plus r of x, a quotient and a remainder we can always find for a polynomial, such that, here's the key, in this algorithm, the degree of the remainder has to be strictly less than the degree of the denominator. Therefore, when we divide both sides of this equation by b now, we're going to get the rational function, which was improper, is now a polynomial plus, by necessity, a proper rational function. So we're going to use long division, and we'll take this improper function and it will create it as the sum of a polynomial plus a proper rational function. And then I can apply partial fractions to this piece. Integrating a polynomial is the power rule. Remember, we want to integrate this. Integral. So the integral of improper is the integral of a polynomial, power rule, plus partial fraction decomposition on the proper rational function. Let's do long division once at least. Okay, so we might as well couch this in what we're actually trying to do. I want to integrate this thing. I see that immediately we won't have to make any partial fraction guesses, because when we use a long division, it will turn it into two things I already know how to integrate because I have a lexicon, hopefully. The derivative of arctan is 1 over 1 plus x squared. So the integral of 1 over 1 plus x squared is arctan x. This is how I know. But first I see degree 3, degree 2. This is improper. So what am I going to do? First, okay. 7 over 3 is an improper fraction of two integers. I use long division to write this as 2 times 3 plus 1. And then when I divide by 3, cancel, cancel, I get 7 over 3 is an integer plus a proper fractional part. I'm going to do the exact same thing to the polynomials. I'm going to now write a as q times b plus r, then b, b, b. We're going to cancel, cancel, and we're going to get this business. How do I do it here? Technically what I do is I use long division. I put 7 here, I put the 3 here. I say how many times is 3 going to 7 without going over 2, and I get 6. I subtract, I get 1. There's my remainder, there's my quotient. I'm going to do the exact same thing here now. X cubed plus x plus 1. When you're doing this in general, make sure you put your other ones in there, but I've done this before. What do I mean by that? You should put your 0x squared in there, but in this one, it's just a baby one, so it won't matter. Make sure everything's lined up. What do I have to multiply x squared by to get x cubed? An x. And then I do that, so I'm going to get x times x squared is x cubed plus x. I subtract, cancel, cancel, bring the rest down. Once I have that, that says this is a degree 0 polynomial, or the polynomial 1, and so that's strictly less, so I can stop. Here you know you stop when the number is less than this number, the quotient. But what that says is x cubed plus x plus 1 is equal to x times x squared plus 1 plus 1. But why did I do that? Because now over x squared plus 1, cancel, cancel, this is now just the polynomial x plus 1 over x squared plus 1. And now, what do I want to do with that? The whole point was this integral now becomes the integral of x dx plus the integral of 1 over x squared plus 1 dx, because I made it proper now. So this improper is the combination of a polynomial plus a proper rational function, and then once we know how to deal with all of our guesses, which we'll talk about in a second, this is now readily integrating power rule, 1/2 x squared plus arctan x plus the constant of integration. This is the idea. Step 1 of partial fraction decomposition, make sure it's proper. If it's not, use long division to make it proper. Next. Step 2 in partial fraction decomposition is going to be factorizing the denominator. I don't care about the numerator. The numerator is only the coefficients to make the guesses for my undetermined coefficients. Once I make the partial fraction guesses, that'll be the next step. Just a second. What our theorem tells us is every degree m polynomial, the denominator, can actually, which is non-trivial, or has a factorization into essentially linear factors or irreducible quadratic factors. This is a non-trivial statement, and the reason why partial fraction works and why they only have essentially 2 guesses is if I can break every polynomial, again, there's some that are extremely hard to do this, try to break x cubed minus x plus 1 into its linear and irreducible quadratic. I know Cardano's formula, nobody said it was going to be nice, but the ones we give you are going to be somewhat readily factorized into these 2 components. I can essentially get powers of x minus a, or I can get powers of an irreducible quadratic. The irreducible quadratic meaning the discriminant is less than 0. Once I can do that, once I made it proper, or even if it was improper, I take the proper part of that now, and I don't worry about the numerator. I factorize the denominator completely. That's what has to happen, because I need to see what the denominator looks like. So we're going to take this and make it look like this if it's proper. Why do we do that? Because once I have all these linear terms to powers and irreducible quadratics to powers, I can now make the appropriate partial fraction guesses to keep everything proper. And then what this is going to do is, I don't know how to integrate this guy right now because they're all stuck together. What partial fractions is going to do is break them up into linear terms of integral of 1 minus x minus a dx plus integral of 1 over x minus a1 to the L1 or L, this type of business. And what is that? And now I know how to integrate this. Natural logarithms, I know how to do this. Negative power rule. And then when we get to irreducible quadratics, completion of squares again. And then we're going to have to use completion of squares and the formula for 1 over x squared plus 1 integral is arctangent. So all of these should turn into the power rule, natural logarithms, or arctangents, or you did something wrong. Let's now make the partial fraction guesses after we've made it proper and factorize the numerator into linear terms and irreducible quadratic terms, factors. Okay, step 3 in the algorithm for doing partial fraction decomposition is you make your guesses. So I've made my function proper. I've now factorized the denominator into linear term factors and irreducible quadratic factors. Once I do that, if I just put a 1 over, so you've got a numerator, but if I have in the denominator somewhere one of these terms or factors, x minus a to the power k, I make the guess these will be all proper because this is a degree 0 polynomial, there's a degree 0 polynomial, degree 0 polynomial over degree 1, degree 2, degree k. So how do I do this? If the exponent is a 7, you do all the way up to the highest exponent over plus 7. But now what that's going to do is if I have to integrate that piece, it will turn it into an integral of just now these separate terms that I can integrate one at a time. This will be natural log. Every other one is the negative exponent rule. So we're done with those guys. And if you have this kind of guy in the denominator to the power L, we make guesses now, but because this is degree 2, our guess has to be linear, 1 less. So this has to be a linear polynomial over degree 2 polynomial all the way up to the highest power. And then what we're going to have to do is step 4 is going to be determining what all of these undetermined guessed coefficients are. Once we find those, then we can finally integrate each of the terms that have been separated this nice way. So the integral of our horrible beast will be an integral of a bunch of these sums, and then we'll deal with each of those sums and how to integrate them, and then that is the entire partial fraction decomposition process. Let's do how we find these. In this stage, I'm going to guess you don't want to see how I get a common denominator of this and this plus that. What's the common denominator? This times this times this times this. Oh, that's going to look horrible, so I'll do it by rote, and I'll do an example of how to find the coefficients. But before we start, I know, and therefore you should know, that how mean I'm being on the exam, it's not a mistake. I know how many coefficients you're going to find, and therefore what the size of the linear system is by knowing what the degree of the denominator is. The degree of b is the number of coefficients I have to find. So if b is degree 3, it's going to be a 3 by 3 linear system I have to solve. What? We'll see in a second. Okay, for these ones, what I'll do is I'll just do the partial fraction guesses and find the coefficients, sort of. But if you want, try to integrate these. That's what I'm trying to do. I'm trying to find the integral of this function, the integral of this function, and the integral of this function. What I'll just do is show you the guesses. The first one, I have 5x minus 3 over, first of all, is it proper? Yes, degree 1, degree 2, so it's proper. I don't have to do any long division. They're all proper because I don't want to talk about properness. We just did. But is this factored? No. What multiplies to give me negative 3 and adds to give me negative 2? What are we going to get? X minus 3, x plus 1. If I did that correctly. So factorize it however you want. Beg, borrow, and steal. Factored now. Now it's prepped for the stage 3 where I make the guesses. I have, now you can see, an a of x over a factorized b of x. Once I've done that, I have 2 linear terms to each to 1 power. So my guesses are going to be, I'm going to guess that this looks like something as a over x minus 3 plus b over x plus 1. I only need 1 of each because each of these are degree 1, so I only have to go up to 1. This one has a power 2, you'll see in a second. And this one has 1 of each, so don't worry. Now what do I mean by that? There's 2 coefficients I'm going to have to find. I knew that already because the degree of this is 2, so there should be 2 factors I have to find here. Here this is degree 2, also 2 unknowns I'll have to find. Here the degree is 3, so this will be a 3 by 3 linear system. So on your exam, and I'm mean, and you see a degree 7 polynomial, oh, that's 7 coefficients you're going to find. Linear algebra will be useful. I have a playlist, I'm pretty sure, about linear algebra. So solving linear systems. Why am I going to need that? Apparently in partial fraction decomposition. Now what do I mean by this? I now have 2 fractional expressions, and everyone's like, well, what do I do? This is the common denominator, first of all, for this. What's the easiest way of getting that? Multiply by what you don't have. This one's missing x minus 3. So I multiply by 1 in the form of x minus 3. This one is missing x plus 1. So I multiply by x plus 1 in the form of 1. Now I have the common denominator. The whole point of that is we can get rid of it on both sides now and look at the Now the numerator comes into play to where I get my system of equations. Simplify everything first, so let's do that. What does that tell me? That tells me that now 5x minus 3 has to equal ax plus a plus bx minus 3b. And then I group everything together. That actually says a plus bx has to, and then plus a minus 3b. When are two polynomials equal? If and only if all their coefficients are equal, and everyone nods. But what does that mean now? This polynomial has to equal this polynomial. So this coefficient has to equal that coefficient. And where's blue? This coefficient has to equal this coefficient. This is x to the 0. This is x to the 1. So I get two equations in the powers of x and the powers of x to the 0. What is my system then? I have in the x1 equation and the x0 equation. In the x1 equation, I have a plus b should equal 5. And then in this equation, I should have a minus 3b equals negative 3. That's how I systematically get my system of equations. If you want, I can augment this matrix and then solve for it. Or what are we going to do? From the first equation, I can see that b is 5 minus a. And then I put that into here. That's the ad hoc way of doing this. If you don't want to use linear algebra for 2 by 2, it works. When you get 3 by 3 or 4 by 4, oh, that game is going to get crazy unless it's sparse and has a lot of zeros. So what do I get from that? First of all, I get that a minus 3 times b, which is 5 minus a, equals negative 3. So I get a minus 15 plus 3a equals negative 3. So what did we get? 4a equals 12. 15 I brought over to the other side. And so what does that say? If I did it right, a is a 3. And then what's b? b is 5 minus 3, which is 2. So I found my coefficients. This is how we find the undetermined coefficients. It becomes a system of linear equations based on setting these two polynomials equal to one another. What does that tell us actually though? This polynomial now, x minus 3, x plus 1, if I'm trying to integrate that, now just becomes what was a? Was a in front of it was this guy. So a was 3. So this says this is the integral of 3 over x minus 3 dx plus the integral of 2 over x plus 1 dx. Now this is substitution natural logarithms. This is the point. Now I didn't know how to integrate this. Partial fraction guesses gave me a way of integrating them term by term. You can finish and fill your boots with that one. I've done it before. It's in my lecture notes. Look it up. Let's do the next one then. So that's if you have distinct roots where you have powers and they're just linear. There's a 1 missing in there, x plus somebody. Those are the partial fraction guesses. Set the two polynomials equal, use the numerator, get your system of equations, find them. If you can't, even if I couldn't find them, I can still integrate this. Just move it to the outside. The integral doesn't care. So if you're stuck and you're like, I didn't say I couldn't find them, but up to the integrals, there they are. It's still a times the natural log of absolute value of x minus 3 plus b times the natural log of x plus 1 plus c. I couldn't find a and b, but there I did everything else you can tell me. Or put hands in the air and quit. Next, the next one, I have 6x plus 7 over, it's proper, I'm already doing it in my head, this is not factored, but so this is going to be x plus 2 squared. What are my guesses going to be? Well, I have a linear term to the power 2, so I guess a over x plus 2 to the power 1 plus b over x plus 2 to the power 2, the highest power appearing. Those are my guesses. It's still degree 2, I'm still going to have to find two coefficients. How do I do that? Get a common denominator. What is the common denominator? This guy, but this one's not missing it, so it's even better when they're multiple roots, because I don't have to multiply this one by x plus 2 once. Now that I have the common denominator, what does that say? That says that 6x plus 7 is equal to ax plus 2a plus b. Again, once I have the common denominator, I can cancel it on both sides and just focus on the numerators. Then I set these polynomials equal to each other. What does that say? In the x equation, that says a has to equal 6. And then it says 2a plus b has to equal 7. So what does that say? Yay! A is 6, and b is 7 minus 2 times 6, which is 7 minus 12, which is negative 5. So I've got the coefficients. If they're nice, you've got them. What does that say? Everyone forgets. You go back, and that tells me that this is a was 6. There's my coefficients, and the idea is we're trying to integrate these things. Natural logarithm, negative power rule, fill your boots. Next one. Okay, for I have a degree 1 polynomial. It's proper, it's factorized, but I have a degree 1 and an irreducible degree 2. You're like, how do I know it's irreducible? Because what's the discriminant? Ax squared plus bx plus c. If b squared minus 4ac is less than 0, I can't factorize this over the real numbers. I can over the complex. We'll see when we do degree 2, order 2 ordinary differential equations. We'll have to play that game one day. For now, what do I have to do? I know that here I have a b is 0, a is 1, and c is 1. So 0 squared minus 4 times 1 is equal to negative 4, which is less than 0. I can't factor x squared plus 1, or look at its picture. It doesn't cross. Its two complex roots are I and negative I, but there's no real roots. It doesn't touch the x-axis. So I can't factor this guy. He's an irreducible quadratic. This is a linear term. What are my guesses? I guess I'm going to give up. No, I'm going to guess I have a linear term, so I'm going to guess a over x minus 1. And now I have one irreducible, so I'm going to guess bx plus c, a linear polynomial over a degree 2 polynomial. What's the degree of this? 3. How many coefficients I'm going to have to find? 1, 2, 3. I can tell before I start, so if it's a degree 7 on an exam, I was purposely being mean, not accidentally. Not accidentally. What do I need with this? I need a common denominator. I should start leaving a space. What's this one missing? X squared plus 1. X squared plus 1. What's this one missing? X minus 1. Now I have a common denominator. I can get rid of it and focus on the numerator. This now tells me 0 times x squared minus 2 times x, plus 4 equals, now what do I have? Ax squared plus a plus FOIL bx squared minus bx plus cx minus c. Group everything together. In the x squared, x1, x0, I'm going to have a system of 3 equations and 3 unknowns. In the x squared, let's use a square for squared, I have a plus b equals 0. Good. That means they're negatives of each other. In the linear terms, I have negative b plus c should equal negative 2. And in the constant terms, I have a minus c should equal 4. I know red pen, blue pen, that guy, he switches them back and forth. I'm not as good yet. Plus mine are Euler colors. Orange pen, blue pen. Patent pending. So now I have to solve a system of 3 equations and 3 unknowns. First of all, it was sparse enough where that says a is negative b. And then, so now what do I want to do? I want to get rid of a and b in one of these equations, or ad hocly solve, or augment the matrix. Another way to do this is I have 1, 1, 0 equals 0, 0, negative 1, 1 equals negative 2, and 1, 0, negative 1 equals 4. So you can augment the matrix, do it that way. Either way, what do we get? Let me try it the ad hoc way. If you haven't seen this, you want to go see some linear algebra, but I'm going to guess most people haven't, and that's why I usually leave it as degree 2 or degree 3. Otherwise, you should see 4 by 4. Good luck with that. So here, I don't have any of the equations that has all 3 in there, but if I subtract these 2 equations, I could probably get something. So let's add those 2 equations. What do I get? A plus c equals negative 2, and a minus c equals 4. See how I got a 2 by 2 system out of the 3 by 3 system? I eliminated b by adding those 2 equations together. So temporarily, what does that say? Now add those 2 equations together. That's going to say 2a. If I added that up, 2a is going to equal 2. So that says what? A is equal to 1. And now I know b is equal to negative a, which is negative 1. And then from there, from this equation, I can get what c is. C is negative 2 plus b. So that is negative 2 minus 1, which is negative 3. That was sort of ad hoc. Hopefully I got them right. Someone will be like, it's not the... Okay, I might make a mistake too, but according to me on the exam, which is I didn't script this, we're just making it up as we go, those are the coefficients I found. If they're wrong, then I'm going to get a bad, oh, you got a half a mark off. Otherwise, I have 3 coefficients. I can now integrate the crap out of my thing. What is that going to be? I now have x minus 1, x squared plus 1. A was a 1, so that should be 1 over x minus 1. And then what were my coefficients? This should be plus. B is negative 1, so negative x minus 3 over x squared plus 1. And then I can integrate. And then we have to deal with this. This actually, we're going to push and make a substitution rule. This is going to push and become arctangents. Either way, let's get to that. Natural logarithm substitution, arctangent, power rule, natural logarithms. Power rule, natural logarithms, arctangents. Now we know how to roughly make our guesses and find the coefficients. Now what can we do? Finally, we can integrate the types of integrals that we're going to get from this decomposition. Let's do that. Finally, what's going to happen is essentially, long story short, and this is why it's so complicated, but once we make our guesses and clean everything up nicely, these are the types of integrals that we're going to be left with. And that's the idea. Instead of them all being multiplied together, we're going to be able to string them out in some way. The only one, the worst case scenario I didn't actually put in there is when we have an irreducible dual power, then I actually have to complete the square and then use trigonometric substitution. We'll do that in another video. That's worst case scenario, is when we have a power. You'll complete the square just like these two, but to get out of that, you'll have to use an arctangent substitution, trigonometric substitution, if it's to a power. So how do I integrate each of these? Hopefully with ease now. The idea is to break them all into these kinds, and then you memorize the kinds that you have. If I have this one, this is the integral of 1 over x minus a dx. If you really want, you can make the baby substitution. This, so dw will equal dx. That becomes the integral of 1 over w dw, which is the natural log of the absolute value of w plus c, which is the natural log of x minus a plus c. Yes, I will allow you to memorize that, because this is going to have, guess what? It's only going to be natural logarithms, power rule, or arctangents are going to be the antiderivatives of these. For the second one, I have a, don't write it like this, write it as a negative exponent. This is the integral of x minus a to the negative 3 dx. If you really want to make the baby substitution, that will be w to the negative 3 dw, with the same substitution, this one. Then what do I do? Power rule. There should be 1 over negative 3 plus 1 w to the negative 3 plus 1 plus c, which is equal to w was x minus a. So this should be negative 1/2 x minus a to the negative 2 plus c. Close enough. Power rule. How do I do the next ones? We're going to have to erase, and I'll be like, what were these ones? We've done those ones. 3. Substitution. I picked this one. If it's a 1, it's arctangent, and then it's, the formula is 1 over a arctan x over a. Why? Okay, well, I have, what this really is I'm missing an a here. I want to factor a squared out. So I'm going to multiply by a squared over a squared. I've multiplied by 1. Now I can factor a squared out of both terms on the bottom. Now I combined those two and factored the a squared out. Now what I'm going to do is make a substitution. The substitution is going to be baby again, but w is x over a. So that says a dw equals dx, which is what I have. So when I make that substitution, this becomes a over a squared, the integral of 1 over w squared plus 1 dw. One of those cancels, and I get 1 over a. Now I take that. This formula is because the derivative of arctan w is 1 over w squared plus 1. The integral of that is 1 over a arctan of w plus c. But what was w? X over a. please memorize that one. That's going to happen a lot. You factorize, get it into this irreducible quadratic, and then you're going to complete the square to make it look like that, x squared plus a squared for something, and then it will be 1 over a arctan x over a every time. Next. All right, for 4, what we're going to do is I see that this is going to be regular substitution rule again. I have a derivative or a function and its derivative up to a constant appearing. So w is going to be x squared plus a squared. Then dw is 2x dx. I don't have that, so 1/2 dw is x dx. What is that going to give me? This is going to give me, with that substitution, a natural logarithm. This is going to equal the integral of 1/2 first of all, and then I have dw over w, which is what? 1/2 the natural log of the absolute value of w plus c. What was w? 1/2 the natural log of x squared plus a squared plus c. I'm getting lazy there now. Edit. What was that? A squared. This, and then everybody, the book leaves it like this. You're like, that's not what I get. Yeah, number on the outside is exponent on the inside. 1/2 exponent is square root. There's the answer, but it's a natural logarithm. Now what are we going to do? The last two are when I have an irreducible quadratic, but it has the middle term. Oh, we're going to have to complete the square first, but then what happens when you make your ax plus b over x squared plus or minus x minus 1? And what happens when we find out that equals the ones that we had? I had x and then plus 1, say, over x squared minus x minus 1. Once I get that, how am I going to integrate that guy? I'm going to split it into the last two cases that I just gave myself. So that case, I'm going to split it into this one and integrate it, and then the last one. Either way, we have to complete the square. This one's going to go weird roundabout in a second. All right, for this one, first of all, what we want to do is ignore this guy temporarily and get rid of this middle term. So I have x squared minus x minus 1. I need to complete the square. So b is -1 over 2 is -1/2. b over 2 squared is 1/4. So I need 1/4, but I can't just add that. That's crazy. So I'm going to add 1/4 and subtract 1/4, which is 0. I can add 0 and not change. So this becomes equal x squared minus x plus 1/4 minus 1/4 minus 1. This is now the completed square. That becomes x plus b over 2 squared, or x minus 1/2 squared minus, I need a common denominator, 5 over 4. What are the roots of those? It doesn't matter. Right now, what do I have? This is also, I see what I did. I just did not the cases I wanted. When I reverse engineered this, we can still leave it in. What have I done? I did specifically, when I had it, I had pluses. I was like, no, that will become irreducible. Of course, this is reducible. I can turn this into 2 linear factors. It'll become the last case. So we have to... The last 2 integrals we're going to do, regardless of what they were, we need the pluses there so that they aren't irreducible. How do I know that's irreducible? B is 1, squared is 1, minus 4 times 1 times 1 is going to be -3. This is not going to factor nicely. So we need the pluses, otherwise it just became one of our other cases. Now what happens? I still do the same thing. I have x squared plus x plus 1. b is 1 over 2 is half. b over 2 squared is 1/4. So it's the same guy, but now this becomes x squared plus x plus 1 over 4 minus 1 over 4 plus 1, which is x plus 1/2 squared plus 3 over 4. And that's where I notice it, because this is a square. This is x plus 1/2 squared plus root 3 over 2 squared. The a here is root 3 over 2 in our formula. Yeah, memorize the arctangent because it's going to happen. So now this becomes, first of all, what do we have? The integral of x dx over x. It became this, x plus 1/2 squared plus, we'll leave it as 3 over 4 for a second. It's going to go reverse, and we're going to get 2 integrals again for a second. Now what I'm going to do is make a substitution to get rid of the shift. W is going to equal x plus 1/2. And what is x? W minus 1/2. What's dx? dw. So now this becomes finally what we want, but it will look like it went round in a circle because I'm going to get 2 terms. This will now be the integral of w minus 1/2 over w squared plus 3 over 4 dx. And now I have to split it again, which is going to be integral of w over w squared plus 3 over 4 minus 1/2 the integral of 1 over w squared plus 3 over 4 dw. Why did we do that? Because now the middle term is missing. Here it's, but once I make the substitution and complete the square, now I can apply substitution rule to this. Now what's it going to be? Let t equal w squared plus 3 over 4. Then 1/2 dt is going to equal w dw. Natural logarithm is this guy. Let me move it up. So from this one now, what I'll do is I'll say t is going to equal w squared plus 3 over 4. 1/2 dt is equal to w dw. This one is arctangent. Why? I just rewrite it as 1 over w squared plus root 3 over 2 squared. And then I can use the formula and this substitution. What does this become? The integral of, what do I get? The integral of w dw was 1/2 dt over, what do I get? T minus 1/2 the integral of 1 over w squared plus root 3 over 2 squared dw. This becomes 1/2 the natural log of the absolute value of t minus 1/2. What do I get? It's going to be 2 over root 3 times arctan of 2 over root 3 w plus a constant of integration. And yes, we're supposed to go back to our original variable x. So what is t? T is w squared plus 1. What was w? W was x minus 1 or plus 1/2 squared. So what does that become? That when you put it all back in, FOIL it back out. I put it back into my nice form, but once you're done, that horrible thing just becomes that guy again. Cancel, cancel, minus 1 over root 3 arctan of what was w? W was x plus 1/2 minus 1/2. So what is that going to be? 2 times x, 2 times 1/2, that will be what? 2x minus 1 over root 3. Let's see. Anyway, as you can see, there's a lot of work to be done there, and that wasn't essentially, was that the worst case scenario? Yeah, that's pretty well the worst case scenario, except for when we do a power of that horrible thing now. What was the last one? 6? We'll get that. And now I see those sort of been reversed because this one's now easier than the last one. Also, it's not increasing order of difficulty. They're just going to be randomly put on exams and assignments too. How do I do this one? Same way, but I need to complete the square. So x squared minus x minus 1. B is negative 1 over 2 is negative 1/2. So I'm going to get, no, those should be pluses so that it's irreducible again. Dang, dang, dang. Otherwise it'll just split into 2 factors. So b is positive 1/2. Almost got me again. Shame on me. Almost. Squared is going to be 1/4. You know what I mean, said George Bush. Fool me once. He couldn't get through it. So what do I do with this? This should be x squared plus x plus 1 over 4 minus 1 over 4 plus 1. This is the completed square, x plus 1/2 squared plus 3 over 4, just like we did last time. So this integral becomes easier. This becomes the integral of 1 over x plus 1/2 squared plus root 3 over 2 squared dx. If you really want, make the baby ship substitution. This will become the integral of 1 over w squared plus root 3 over 2 squared dw, which is 2 over root 3 arctan of 2 over root 3 w. What was w? X plus 1/2, so we'll FOIL that in there, plus a constant, equals 2 over root 3 arctangent of 2 times this will be 2x plus 1 over root 3. Let's see. This is how we do partial fraction decomposition. Step 1, make sure it's proper. Step 2, or use long division to make it proper plus a polynomial. Step 2, factorize the denominator into its linear factors or irreducible quadratic factors. Step 3, make your guesses for partial fraction decomposition. Step 4, find your undetermined coefficients. Once you have that, step 5 is integrate these in those order, and then that should be the worst case scenario. Try for yourself the integral of 1 over x squared plus x plus 1 squared dx. Complete the square and then trigonometric substitution. Please subscribe right here, hit the notification bell. I'll see you next time.